Yes, questions? Well, the moral of the story of the last thing that we had done was basically, at least in one dimension, the solution, the value of the solution of the Laplace's equation at a point is equal to the average of its values at symmetrical points from the center. The same holds also in 2D. If you have the Laplace's equation, if you have a solution of the Laplace's equation, then the value of phi, let's say at the point R, is nothing but its average. But of course, in one dimension, the symmetrical points just form 2 points. If you are on a plane, the points that are symmetrical or at the same distance from a given point, they form a circle. So when you are taking the average, you have to be talking about the average over a sphere, over a circle, sorry. Let's say R plus delta dot dl 1 over 2 pi r. Where here the circle, you have the xy plane. This is the point R, and the loop that you are considering is this one, which has a radius r, and the positions I have denoted by delta. So I'm just integrating phi over this loop around the point R, and I'm summing over all the values of phi on this loop, and then dividing by the circumference of the loop. That is what we call the average. Now, in 3 dimensions, we will generalize to the area. Well, we will not do the proof for 2D, we will do it for 3D, but in 2 dimensions, the Laplace's equation also has a different physical meaning. Let's just take x, y, and z. Okay, this is not 2D, this is 3D. But let's just imagine we have some kind of a loop of an arbitrary shape. This is a 3-dimensional loop. So I have, for example, you just take some wire, give it an arbitrary shape. It doesn't have to lie on a plane. Assume it is rigid, so it will not be deformed. Then I take a balloon, I stretch the balloon on this frame. And the balloon will take a shape. And the shape of the balloon, or stretch an elastic film on the rigid frame. Or you can just imagine a soap bubble formed in this plane, not in this frame. Then the bubble or the elastic sheet will have some shape. It will have a smooth shape. And that shape you can actually specify mathematically by writing the height. So this is z, the height as a function of x and y. So this is how I can specify a surface in 3 dimensions. That is one way of specifying the surface. And then this function f satisfies the Laplace's equation. Of course, assuming the surface is sufficiently flat. Now, there are some modifications to this equation, to the Laplace's equation, but approximately the shape will satisfy the Laplace's equation. So this is also one way to see that you cannot really have a local bump or a local well in the solutions. Just imagine an arbitrary frame. Imagine you have created a bubble on that sheet. And the bubble will not just go up or down unless you apply some pressure. It will be just smooth without any local maxima or minima.
Yani hocam bunu şey mi yaptık böyle? Plane'in görüntüsünü mü aldık?
The image on the plane is this one. This is the image in the plane. On top, you see, this is my frame, right? I can take a projection on this plane. This is the projection on the plane. Well, if I know the height of this elastic sheet at every point, then I know the surface. Well, this is the physical interpretation. May I take a jacket, T-shirt, or something from one of you? You also come here. You come too. Hold. No, hold it. We will be stretching it. So you see, okay. Assume this is an elastic sheet or a soap bubble. No, you keep lift that hand up a bit. So you can give it arbitrary shapes, but there is no local maximum or minimum. You will never be able to create a local maximum or minimum. Of course, here there is a local maximum, but that is because this is not an elastic sheet. This is what I mean by the surface will be specified by the solution of a Laplace's equation in 2D. No matter what the frame is, the shape of the frame is, you can just give it any frame. There won't be any local maximum or minimum. Lift one hand, lift that hand. Okay, so if you look at this one, it looks as if these points have a local maximum. But even those points don't have a local maximum. If we pull it down, along this direction, it bends slightly down. This is a local minimum along this direction. But in the other direction, it has this shape. It has a local maximum. So in one direction, it has a local minimum. In the other direction, it has a local maximum. That is what we call a saddle point. It is not a local minimum or a maximum in 2 dimensions. Okay? This is the physical picture of the Laplacian in 2D. That is easier to visualize. Now let's go to 3D. Now, we will not be directly looking at the Laplace's equation. What I will first try to prove is that, well, we will still prove that the potential at the position R is equal to the surface integral of the potential divided by 4 pi r squared. No, not 4 pi r squared, it's 4 pi r squared, where the surface is a sphere of radius r and center at the position r. This is what I will try to prove. Now, of course, since we are looking at the solutions of the Laplace's equation, there shouldn't be any charge in our sphere. Because if there are charges in the sphere, then it's no longer a solution of the Laplace's equation. Now, the phi, I can always write as the potentials created by point charges. So if I prove the above claim for a single point charge, then I can prove the claim for the total potential. So that will be my strategy. So rather than looking for an arbitrary potential, I will look at the potential created by a single point charge. So this is the question I have now. I have this sphere, and somewhere outside my sphere there is a point charge. And this point charge is creating a potential on the surface of my sphere. I will prove that the average of the potential on the surface of my sphere is equal to the value of the potential at the center of my sphere. That is what my claim is, the thing that I will be trying to prove now for a point charge. Because once I prove that, since the value at the center can be anywhere, this sphere can be anywhere. The only criteria is that the charge should be outside my sphere. This sphere can be anywhere, it can have any radius. And if I prove that whichever sphere I choose, if I can prove that the average of the potential on the surface is equal to its value at the center, that also completes the proof that the potential cannot have a local maxima or minima. So that will be the end of my proof. And then I will use this fact to prove other stuff, like the uniqueness of the solutions. That is where we are trying to head to. Now, if you want to calculate the average, first we should choose some coordinate axis. Well, for simplicity, let's put the origin of our coordinates at the center of the sphere. This is the origin. This is my z-axis. Let's say this is x, this is y. It is at a distance, let's say, d. I can choose my coordinate axis whichever way I like. So I'm just choosing it to simplify my notation at least. So I saw that the charge is located along the z-axis. Now let's consider this point. Let's try to write the potential at this point, r. Phi at the point r is equal to, what's the potential created by a point charge at this point? One over 4 pi epsilon 0 q over this distance. This is the potential. Which is 1 over 4 pi epsilon 0 q over square root of r squared plus d squared minus twice r d cosine theta. Well, this is the r minus that we were talking about in the first hour. Now we have to take the surface integral of this phi over the surface of the sphere. Now on the surface of the sphere, ds is nothing but r squared sine theta, d theta, d phi. It just looks like the volume element, but the dr is missing. This is the surface element on the surface of the sphere. Does everybody know this ds? If not, we can discuss how we obtain that ds. In spherical coordinate, yeah. So this is equal to, the surface integral is now sine theta, d theta. Theta goes from 0 to pi. D phi, phi goes from 0 to 2 pi. I am covering all of the surface, times r squared times 1 over 4 pi epsilon 0 q over square root of r squared plus d squared minus 2r d cosine theta. Well, nothing depends on phi. I can just evaluate the phi integral. That will just give me a 2 pi r squared. I have 4 pi epsilon 0. From 0 to pi d theta, q I can take out. sine theta divided by square root of r squared plus d squared minus 2rd cosine theta. Well, this small r is actually large r because I'm on the surface of the sphere. And the surface of the sphere has a distance capital R from the center. Let's evaluate this integral. This is 2 pi r squared q over 4 pi epsilon 0 from 0 to pi d theta. Let me write that term as the derivative of r squared plus d squared minus 2rd cosine theta. Now, if we look at the derivative of this square root, because of the square root, when I take the derivative, I will have 1/2. Then I will have the 1 over this square root. Then I will have the derivative of all of this term with respect to theta. I'm just using the chain rule. But the derivative of all of this term just gives me 2rd sine theta. Well, I have this sine theta. I have this additional 2 over here, but from the derivative, I also get an additional 1 over 2, so there are no numerical factors. But there is this additional rd term, so let me divide by 1 over rd. So this derivative is equal to the sine theta over the square root. But now this is the integral of a total derivative, which is trivial to evaluate. This is equal to 2 pi r squared q divided by 4 pi epsilon 0, 1 over rd times the square root of r squared plus d squared minus 2rd cosine theta, when cosine theta goes from 0 to pi. So the integral of phi over the surface is, let's make some cancellations, 1 over 2 epsilon 0 r q over d times, well, when theta is equal to pi, what is cosine? Cosine is minus 1, so we get the square root of r plus d squared minus when theta, no, not cosine, theta is equal to 0. What is the cosine of theta? 1. So it is the square root of r minus d squared. This is equal to qr over 2 epsilon 0 d r plus d minus r minus d, absolute value. Now let's go back. We had assumed that we are looking at the case when the charge is out of my sphere. So d is larger than r. Well, if d is larger than r, then I can take that this absolute value of r minus d is just d minus r. R plus d minus d minus r. So this is equal to qr over 2 epsilon 0 d. Well, these will cancel. I will be left with 2r. These 2's will also cancel. We are left with q over epsilon 0 d times r squared. Or let me rewrite this. ds phi is equal to q over 4 pi epsilon 0 d times 4 pi r squared. Or 1 over 4 pi r squared ds phi is equal to q over 4 pi epsilon 0 times 1 over d. Yes. I'm integrating over a surface. Now, one point that you should pay attention to, though, Here I'm not writing this the surface vector. This is not a vector integral. This is just a number. From the beginning, I'm only considering the scalar area element, not the vectoral one. But you see, this is nothing but the average of phi over the surface. I'm integrating it over the surface dividing by the total surface area. This is the average of phi. But this is nothing but the potential created by this point charge q at a distance d, but my center is at a distance d from my point charge. So this is the average of phi on the sphere. This is the value of this is the potential at the center of my sphere. So kind of I proved what I was trying to prove. The average of a potential, electrostatic potential, in a region where there are no charges is equal to the value of the potential at the center of the sphere. This was for a point charge, but if I have a continuum charge distribution outside my sphere, I can just write it as the sum of point charges. So this is kind of all of the proof. Because I'm taking an average. Average is just summing the values at every point. It's just like in the one-dimensional case. I just added the values. I'm not subtracting them, I'm adding them. In the 3 dimensions also, I don't care about the direction, I'm just adding the values. That is why I don't have the vectorial ds. And this is what we prove. If we add the value of our potential at every point on the surface and divide by the surface area, in that case we get the potential at the center. Well, you see, this is for a point charge. This would be more precise. But you see, if we have a sphere, and there are many charges over here, qi, again out of my sphere, then phi I would be not phi, the total potential, will be nothing but the sum over phi I at the point R. Let's say this is the location of this point is, let's denote it by capital R. What we had proven is that if we integrate this phi R over this surface of the sphere, this I can always write as the integral of phi I over the surface of the sphere and summing the results of the integral. Let us also divide by 4 pi r squared. This is equal to, well, each one of these is nothing but the value of my potential at the center of my sphere. But this is nothing but the total potential at the center of my sphere. This was the last step that I didn't write. So whatever charge distribution I have, not necessarily a point charge, whatever charge distribution I have, if I take its average over the surface of a sphere, it is always equal to the potential at the center of my sphere. And again, just pay attention to the fact that this value over here doesn't depend on the size of my sphere. You can choose a sphere of arbitrary size as long as there are no charges inside your sphere. That is the critical thing. Because if there are no charges inside the sphere, the potential satisfies the Laplace's equation. Well, let's see what happens if there is a charge inside the sphere. Let's look at that one also. I will again my strategy will again be the same. I will start by a single charge inside my sphere. A single charge inside. I will again choose my coordinate axis like this. The previous derivation I did here, I don't need to change anything except then when I obtain this result over here. Now, this is my D. This is R. So in this case, D is less than R. So this is equal to QR over 2 epsilon 0 D, R plus D, minus R minus D, well, this time the R's will cancel, and I'm left with QR over 2 epsilon 0 D times twice D. Now these also cancel, 2D. Now if I take the average, well, the interesting thing here is that, you see, the final result, the average of the potential, is still independent of the position of my charge. In this case, it's independent of the position of my charge. Wherever my charge is inside the sphere, the average of the potential that it creates over the surface of the sphere is just a constant. So if you calculate the average, (4 pi r squared), this is equal to 1 over 4 pi epsilon 0 q over r. So basically, phi, if we have many charges, phi we can write as the sum over the potentials created by each point charge. If we take the average of phi, this is equal to, over the sphere, this will be equal to the average of the potentials created by each point charge summed over. But this is equal to, now for charges inside my sphere, the result is nothing but 1 over 4 pi epsilon 0 qi over r, r being the radius of my sphere, plus qi outside my sphere it is the value of phi I at the center of the sphere. So the average, let me just denote it by this one, over the sphere. Just notation. I mean, this I will use to denote the average. This is equal to 1 over 4 pi epsilon 0, q enclosed divided by the radius of the sphere, plus the potential at the center of the sphere. Let me just put a prime over there, where phi prime is the potential created by other charges. by charges outside my sphere. So this is kind of the external potential. So there are some charges inside my sphere, plus there are some external charges, and the average of the potential over the sphere is nothing but the value of the external potential at the center of the sphere plus 1 over 4 pi epsilon 0, the total charge inside divided by r. Now this result will be important when we study the electric field in matter. Because then what we will be really interested in, for example, if you are inside the matter, if you just look at the potential at the position of an electron, well, it should diverge. But just at the nearby point, it should become very small. So you don't want, you are not really interested in such huge fluctuations. What you are interested in is just the average value of the electric field or the average of the potential. And this is how we will be evaluating the averages. Yes? What will serve our purpose? Now we have proven that if there are no charges inside my sphere, the average of the potential on the surface is equal to the value at the center. But this proves one thing: the potential cannot have a local maximum or a local minimum. So we were trying to prove that one. It cannot have a local maximum, it cannot have a local minimum. But if we want to show whether a function has a local maximum or a local minimum, we have to compare its value at a point with its value at nearby points. So that's why we are looking at the surface. No, the potential. No, here we are talking about the potential. Yes? That's your question? Sorry to interrupt. There are no charges on the surface. There are no charges on the surface. Yes. Let's rephrase it. We are not saying that the potential at the surface is equal to the potential at the center. We are saying that the average of the potential on the surface is equal to the potential at the center, the average. So that if on the surface, let's say, some point has a value larger than the value at the center, then the average should be equal to the value at the center. That basically tells us that if one point has a value larger, some other point should have a value smaller. But that is kind of tells us that it cannot be a local maximum or minimum, because for a local, let's say local maximum, every point nearby that is not at the center has a value smaller. But this theorem tells me that that cannot be. If one point nearby has a value smaller, some other point should have a value larger than the value at the center. Which will allow me to prove something else now. So we are kind of trying to go for a proof, and this is some result that we will need intermediately. That there are no local maxima and no local minima.
Hocam bu dediğimiz şey Laplace equation'ın sonucu değil mi?
Yes.
Sonucu.
Yes. If we have the solution of the Laplace's equation, then it cannot have a local maxima and a local minima. Now, where did we use the Laplace's equation? Well, basically when we say that the phi is just the summation of the point charges, and for a point charge, we said that this is phi. When we said this one, we already used the Laplace's equation. So once we have the Laplace, now writing this is the solution of the Laplace's equation. So once we have a solution of the Laplace equation, it cannot have a local maxima or a local minima.
Hocam bu kürenin içi dolu olsaydı mı?
Those things we will study when we study electric fields in matter. the sphere doesn't exist. You see, we have a point charge over here. I'm imagining this sphere over here. This is just like a Gauss surface. It's a mathematical surface. At some point outside my sphere, there are some charges. Since they are outside my mathematical sphere, inside the sphere, the potential satisfies the Laplace's equation. And if it satisfies the Laplace's equation, its average on the sphere is equal to its value at the center. Now, for the time being, we are looking at electrostatics in vacuum. The only things we have are the point charges we put wherever we like. It doesn't exist. It's a mathematical object. By the way, it's not even an arbitrary surface. It has to be sphere. If it is not sphere, our proof does not hold. Well, you see, the solution of the Laplace equation is independent of this surface. So you can talk about the Laplace equation without considering any surface whatsoever. But what we have proved here is, if you have a solution of the Laplace equation in a given region, if you imagine a sphere, it only holds for a sphere. If you imagine a sphere in this region, the average of the solution of the Laplace equation in the sphere gives you the value of the function at the center. That is what we have. This doesn't hold if you have an arbitrary other surface. It doesn't hold if you have some charges inside the sphere, etc. No. No. Why should it? No. Why should it? I mean, we are making a precise statement over here. If you take the average over the sphere, it is exactly equal to the value at the center. If it's not a sphere, you cannot make such a precise statement. If you take the average over an arbitrary surface, you can probably prove that there exists a point in this volume for which the average on the surface is equal to the value at that some point. You can prove the existence of that point, but that's all you can do. No. I mean, this is enough to, I mean, you see, a function can have a local maximum or can have a local minimum, independent of whether you talk about such surfaces or not. I mean, I can talk about I can imagine such a shape. I can say that, okay, so there seems to be a maximum at this point, for example. I don't need to imagine a sphere. But this theorem proves me that for this solution, there cannot be a local maximum or minimum. I mean, if I can prove such a statement for the arbitrary surface, well, I can also use that arbitrary surface, but this much is enough for me. To talk about the local maximum or the minimum of a function, I don't need to talk about the average on the surface of a sphere. But if I have this theorem, I can use this theorem to prove that there are no local maxima or minima. This is enough for me. I mean, you can probably prove more stronger theorems, stronger constraints, etc. But what will be the point? If you're only interested in proving that there are no local maxima or minima. This much is sufficient. And in this theorem, the only thing I will use about the result of this theorem is that the solutions of the Laplace's equation cannot have a local maxima or minima.
Zaten bunun solution'ı şey değil mi hocam? Harmonik function.
So, which means? Well, sine is a function of a single variable. This is the solution will be functions of 2 or 3 variables. They are still called harmonic, but I will not use that name. That is what I need. So what I am claiming here, let's have an arbitrary surface. It can be an arbitrary surface this time, not necessarily a sphere or any other particular shape. Inside this volume, there are no charges. Well, the only thing I need is that the potential satisfies the Laplace equation inside the volume. If phi is a potential, it just tells me that rho is 0. And on the boundary, this is the boundary of V, phi is equal to 0. Just again, imagine the stretch film example. You have your frame, you put it on the xy plane. Well, all the points on this elastic band or in this bubble will lie on the xy plane. They will not go out of the xy plane, so it will be completely flat. That is what we mean by phi is exactly equal to 0. Because if your function is, let's say, has exactly the same value at every point in this region, if, let's say, at some point it takes a non-zero value, it means, let's say, it has a positive value at this point. Well, it just means that your function started from 0 all around, but it should go above. It should take positive values. But then as you go to the other end, it should go back to 0. But that is a local maximum. And it cannot have a local maximum, so it cannot have a positive value here. So this is just a direct consequence of the fact that the solutions of the Laplace's equation cannot have a local maximum or minimum. So if they are 0 on the boundary, then the solution is 0 everywhere inside your volume. Do you agree? Well, we are talking about the Laplace's equation. So if phi is the potential corresponding to a charge distribution, it just tells me that the charge inside my volume should be 0. Since charge is 0, exactly 0 at every point, Q is 0. Let's see. Let's see how we will use it. Now, what we mean by uniqueness theorem? We will assume that we have some volume V, and it has some boundary. Inside we have some charge distribution, not necessarily 0. It doesn't have to be 0. And let's say that somebody claims that they have 2 solutions for the potential. Phi 1 of R, such that the Laplacian satisfies minus rho of R over epsilon 0, and phi 2 of R, which is minus rho of R over epsilon 0. So we have 2 solutions. And they say that phi 1 of R is equal to phi 2 of R if R is on the boundary. They satisfy the same boundary condition, and they both satisfy the Poisson's equation. Somebody just comes to you and say that, okay, so you had this boundary problem where you are required to find the potential corresponding to this charge distribution inside my volume subject to this boundary condition. And they say that they have two different solutions. Is it possible? Now, the uniqueness theorem tells that it is not possible. If you have one solution, that is the only solution. There is no second solution. That is what we are going to prove. Well, the proof we had actually done. Let phi is equal to the difference. Well, the Laplacian of phi 1 minus the Laplacian of phi 2, which is minus rho over epsilon 0 minus rho over epsilon 0. This is equal to 0. So this difference of these potentials satisfies the Laplace equation. And phi of R, when R is on the boundary, this is phi 1 of R minus phi 2 of R, but they satisfy the same boundary conditions, so they have the same value on the boundary. So this difference is 0 if R is on the boundary. So we are looking at in a region of space in which we are looking for a function that satisfies the Laplacian. Furthermore, at the boundary of this region of space, the function is 0. Go back to our corollary. If you have a function that satisfies the Laplacian, it is 0 on the boundary, then it is 0 everywhere in your volume. But if our function phi is 0 everywhere in our volume, then phi 1 and phi 2, they have to be equal. This is the uniqueness theorem. So if you find one solution of your boundary equation, the Laplace, if you are looking for a solution of the Poisson equation subject to a given boundary condition, there exists only one solution. This is where we were trying to arrive. You cannot have two different solutions. So basically, the way we will be using this is, first we will identify the boundary conditions we have. Then we will try to guess some solution. Just guesswork. We have some certain methods, certain tools to guess a solution. If we can guess a solution, then that is the only solution. In our guess, we will be making some assumptions, approximations, etc. But if we can finally obtain a function that satisfies our Poisson equation and our boundary conditions, then our assumptions and approximations, etc., have to be correct. That is what we will be doing. Yes? No, you see, in this problem, I'm not saying that there are no charges. I'm saying that there are charges everywhere. There can be charges everywhere. I don't really care. What is important is if I take the difference just looks as if it is the potential of zero charge. The difference doesn't satisfy the Poisson equation. It satisfies the Laplace equation. And we already know that the solutions of Laplace equation cannot have a local maxima or minima. And that is enough for me. I have proved that this phi over here is exactly 0. You see, in this result, what we had said is if we have a function that satisfies the Laplace equation, that is the criteria. What is this function? I don't know. It can be the potential. It can be the shape of the surface, etc. I mean, I don't really care about the physical interpretation of that function, whatever that function is. As long as it satisfies the Laplace's equation, and also it is 0 on the boundary, then it has to be 0 everywhere. Well, this Laplace equation you will see when we are studying electrostatics. The electrostatic potential in a region which doesn't contain any charge, then we have the Laplace equation. Or if you study, let's say, the shape of surfaces, then you end up having Laplace equation. Wherever you end up having a Laplace equation, if your function is 0 on the boundary, then your function is 0 everywhere. And I use that result in this case. Well, phi1 or phi2, they do not satisfy the Laplace equation, but the difference does. So now I have a function that satisfies Laplace's equation. Furthermore, it is 0 on the boundary. So it has to be 0 everywhere. That is what I use. What is phi? Well, the difference of phi1 and phi2. I'm not giving it a physical interpretation. Phi1 and phi2, I'm giving them physical interpretation. They are the potentials created by the charges, both inside and outside my volume. But phi, the difference of the potential. What name would you like to give them?
Yani böyle yaparak hocam içi boş bir hacim mi düşünmüş oluyor?
Not really. I mean, my volume contains charges. You see, in my volume there are charges. And these charges are creating potentials phi1 and phi2. I'm not considering a case where I have 0 charge in my volume. But since these satisfy the Poisson's equation, their difference satisfies the Laplace equation. That is all I need.
Mesela şu bir tanesi 2 rho olsaydı o zaman.
No, you see, the physical case of phi1 and phi2 is that you are given your physical system. You are given your volume. There is a charge distribution. Okay? And then I come to you and tell you that, look, I have this function and this function. They are both correspond to the potential created by the same charge distribution, exactly the same charge distribution. And if I claim that these two functions are different, you can say that I'm wrong. You don't even need to look at the functions. Because you already know that if given the charge distribution, given the boundary conditions, we are not changing them, there exists a unique potential, a single one. There cannot be two different ones. I mean, somebody can obtain the potential using different means. They can look completely different, but they have to have exactly the same values everywhere inside your volume. This is what we had proved. And as I said, especially when we study the method of images, for example, basically method of images is just a way of guessing the potential. You make some guesses. And if you can show that it satisfies your boundary conditions, and also it satisfies the Poisson's equation, if you can show that your guess satisfies these conditions, then it is the only solution. You could have just go out and try to obtain a solution using more complicated means, but at the end you should obtain exactly the same solution.
Hocam peki şu uniqueness teoremde o Laplace equation'ı kullanmamızın bir şeyi var mı? Amacı var mı? Sonuçta şu phi 1 eksi phi eşittir 0 dediğimizde de orada eşit olmaları gerektiği çıkıyor.
Yes, but how do we say that phi should be equal to 0? I could say that phi is equal to 0. Well, this is the boundary. This is only on the boundary. They can be different in the value. But since phi satisfies the Laplace's equation, that is where I'm using it. Phi satisfies the Laplace's equation, plus it is 0 on the boundary, so it has to be 0 everywhere. That is where I'm using the Laplace's equation. Well, you have other courses probably. They are going to kick us up. See you next week. We don't have a lecture on Friday.